Hello everybody, this is our video for problem 1C from quiz 8, and we have another series. We're going to detect whether it converges or diverges, and in this case I think a pretty reasonable approach is to look at the underlying sequence, note that you almost have a rational function of n. Yeah, there's a square root, but that doesn't really bother me a whole lot. I see that the numerator and the denominator have powers, highest power of n, 1 and 3, which tells me the underlying sequence is going to converge to 0. And this underlying sequence should be asymptotically equivalent to 1 over n squared. And 1 over n squared has a series which converges by the p-test, so this thing should converge. Okay, that's like the very first thing I'm thinking. I got to write it all down still, but that's what I'm thinking as I go. Okay, so let's set up the limit comparison test. All right, so for the limit comparison test, first thing, I need to make sure that each of the numerator and the denominator I want the whole thing to be eventually positive, right? But if I can see that both the numerator and the denominator are eventually positive, then their ratio will be eventually positive. Okay, so we have here 5n minus 4. Of course, when n gets large enough, it will be positive, and well, look, when n is 3, we're already at 15 minus 4. So that's 11, right? So this is at least 11 for n at least 3. And 2n cubed plus the square root of n, well, again, for n positive, like this is always going to be positive. So this is positive for n greater than 0. And therefore, the quotient, fn 5n minus 4 over 2n cubed plus the square root of n is eventually positive. Okay, now what I believed is that this underlying sequence is asymptotically equivalent to 1 over n squared. And 1 over n squared is, of course, always positive. Right? Well, of course, we don't want n to be 0 here. Okay, so that means that as long as I can actually show that these two sequences are asymptotically equivalent, then I'll be able to use the limit comparison test. So to show that these are asymptotically equivalent, I'm going to go to the limit 5n minus 4 over 2n cubed plus the square root of n. And I want to divide by 1 over n squared, which is the same as multiplying by n squared over 1. All right, let's do a little bit of work here. So I have 5n cubed minus 4n squared over 2n cubed plus the square root of n. Okay, and maybe it'll be helpful. I can write maybe the square root of n is n to the 1/2, because I'm going to factor out now an n cubed from both the top and the bottom. So on the top, I have an n cubed times 5 minus 4 over n. And on the bottom, I have an n cubed times 2 plus, okay, let's see, a half minus 3, because I'm factoring out an n cubed. That'll be 1 over n to the 5/2 power. All right, so if I multiplied this back in, right, I'd have 3 minus 5/2, which would be 1/2. Okay, now as n, oh, well, first I can notice, right, the n cubes go away. So let's get rid of those. So I'll have 5 minus 4 over n over 2 plus 1 over n to the 5/2. And as n goes to infinity, 4 over n goes to 0, and 1 over n to the 5/2 goes to 0. And so this limit is just going to be 5 over 2, which is definitely a positive constant. So this implies that the sequence 5n minus 4 over 2n cubed plus the square root of n is asymptotically equivalent to 1 over n squared. Now we know by the p-test with p equals 2 that the series, and let's see, where were we starting at? 3? Yeah. The series starting from 3, 1 over n squared converges. And therefore, by the limit comparison test, the series starting at 3, for 5n minus 4 over 2n cubed plus the square root of n also converges. Okay, now this would be my preferred way of solving this problem, but another reasonable way to attack it would be using just the regular comparison test. So let's make a little observation here. So we're going to use the comparison test now. So if I start with 5n minus 4 over 2n cubed plus the square root of n, if I get rid of this square root of n, that is going to make the denominator smaller. But if the denominator is smaller, then I'm going to be making the fraction bigger. So this is going to be less than if I had 5n minus 4 over 2n cubed. Okay, what if I got rid of this minus 4? Well, the minus 4 was making the numerator smaller. So getting rid of it, that's like adding 4, will make the numerator bigger, which will make the fraction bigger. So this is less than 5n over 2n cubed. Okay, again, n is not equal to 0. So it's okay to cancel. And I'm going to get 5 over 2 times 1 over n squared. And now we know, again, by the p-test, with p equals 2, we know that the sum, n goes from 3 to infinity, 1 over n squared converges. Of course, multiplying by 5 halves doesn't change that. So I can put a 5 halves in here and just change what it converges to by, well, a factor of 5 halves. Okay, but again, we already know that this underlying sequence is eventually positive, and so we can apply the comparison test. Since this underlying sequence is less than this underlying sequence, we know by the comparison test that the series for 5n, put over here, 5n minus 4 over 2n cubed plus the square root of n also converges. So there's another approach that we can take. Again, I prefer the limit comparison test just because I can see very quickly what the answer is going to be. Whereas the comparison test, I almost feel like I have to get lucky, right? That, I have to think real hard. Okay, I get rid of the root n. That's going to make the fraction bigger. I mean, what if this had been a plus 4, right? That definitely would change the way I have to attack this problem. So again, I usually like to start using the limit comparison test, but there's nothing wrong if you can see, right, how to use the comparison test. And you can see it's also generally going to be a shorter approach, all right, if you can do it that way. All right, we will see you next time.